Today we are going to have lecture. Okay, this one first. This one. Okay, live yet. Live. Can hear? This one, this way. Okay, should be recursive. This one. Okay, something I need to clarify. Okay, see a bit softer than usual. Increase. Yeah, how about now? I move my mic closer. I hope you can hear better. Yes. Okay. Today 145 student. I hope it's a student. Okay, not bad. Okay, one thing I need to clarify. I made some small mistake on Monday. The last things I mentioned about this. Okay, when I talk about this, we back to where we stopped on Monday. Yeah, when we're trying to analyze this algorithm. This algorithm basically trying to do some search. Okay, given A in the slide and the lecture notes, we assume that A is always in the item list. In other words, in this example, on the right hand side, this example means that A definitely is either 1, 2, 3 or 4. In that scenario, and then we know that the time complexity in the first line is C1. You take constant times to do this assignment, constant time. So what is the best case? The best case is like when your A is equal to 1 in this example. That means this thing you have no chance, because if it's your key equal to A, then you have no chance to enter the while loop. In that scenario, we will consider is the best case. Then that means the complexity, you just need to take C1 when A is the first item in the list. That is the best case. Worst case, if A definitely is inside the list, the worst case very likely is your A is equal to 4 in this example. That means you need to go through the whole linked list to search every item. Then in the end, the last item is the one you look for. In that scenario, you will find that you need to run n-1 iteration. Because the first one you compare, you run. Then when you reach the last one, they are equal. The last nodes, you won't enter the loop, because once it's equal, you will stop the while loop and return. So you will take n-1 iteration. So that is the worst case scenario when we assume that A is in the list. The mistake I make is, average case, you just, this one I already explained. The thing I make the mistake is when we consider A is not in the list. When I consider that, there's a pen. When I considered, maybe if I generally, of course, assume A is in the list, maybe not good enough. Worst case is the last item. That is the assumption Kai Xiang said. Best case is the first item, worst case is the last item. But take note that this is, I assume A is definitely in the list. Then on Monday, I mentioned that what happened if I considered A is not in the item list. If can be not in the item list, it's possible in practice. So I need to consider the probability when A is in the list. A is in the list. Sorry, I don't have the pen to write. Yeah, in the list. In list. Okay, there's a probability. Normally, it depends your search space vs your item you have to decide the probability. If, for example, if I'm trying to consider my A can be from 1 to 200, in my list only have 4 items. That means this one is maybe 4 out of 200. If I only can search from 1 to 200, yeah, then in other words, those are not in the list. If all are equal chance, that means I got 196 out of 200. I will search something not in the list. If all the I randomly select the number from this 200, from 1 to 200, yeah, that is the scenario when A not in the list. When A not in the list somehow. Okay, this is the probability. Then, what is the cost for when A is in the list? This is the average. The average case, yeah, here, when A is in the list. Yeah, the mistake I make is here. What is the worst case? When A is not in the list, you find that it's always the worst case. What happens if A is not in the list? What does it imply? That means when you search, you will search from first item to the last item. From here, all the way you will search. Yeah, it's not A. This one also not A. This one also not A. Yeah. Then you will search one more times. Yeah, because this is a null pointer. So it's not A. When this key is 4, your A, let's say, is 5. Yeah, actually you will enter to this and then go to here, to line 4, and then find out that the next one is the null pointer. So you will break. So in that scenario, actually this one is C2 plus n. You run n iteration actually. You run one more iteration than this case, because you will enter into this and run one more iteration and then get out from this point at line 4. So actually that is the time complexity when A is not in the list. Yeah. Monday I make a mistake. I said they are the same. Actually they are not the same. This worst case is only checked to here only. Then they already found. But if it's not in the list, they need to check this is a null pointer. Then they stop. So they need one more extra iteration. Okay, I hope I already clarified the doubt. Okay, so today, okay, this is the last Monday lecture. Okay, this class. So today we will carry on the analysis. We're trying to analyze C1. Yeah, for when A is not in the list. Yeah. Am I? What? Yeah. So is C1 plus n, because when A is not in the list, actually you'll find that you run n iteration. Okay. So today, okay, we will carry on the analysis, but now we're trying to analyze the recursive function. So this part, you will learn how to express the time complexity of the recursive function in terms of recurrent equation. Yeah, so you will learn a few. Okay. Yeah, you were trying to write out the recurrent equation for the time complexity of the recursive function and trying to solve it and get the time complexity function of the recursive function. So what you need to do, generally speaking, for a recursive just now the example, okay, Jefferson Lee said, yeah, the base case C1 plus C2. C1 is the first line, is line 1, the line 1. Then C2 is the cost for each iteration. Okay, back to this. So you give you a recursive function. What you need to do, you need to know that the recursive function in each recursive call, you need to do how many primitive operation. You need to know the number of primitive operation for each recursive call. Okay, then of course you need to know how many recursive call are there. Then that is, once you have these two components, you will be able to find out the time complexity of the recursive function. Okay, maybe we try an example to calculate the factorial. So in this factorial, we're trying to calculate the factorial. We have I want to calculate this by using this recursive function. Yeah, that means this one, what it's trying to do, yeah, every time, if your n is greater than 1, you will come to here. That means you are trying to n times, then you call the n minus 1 factorial. So recursively, this part trying to recursively call. Then every time your problem side will reduce by 1. Then, not surprising, you keep doing this. Eventually, it's n times n minus 1 times n minus 2, and so on and so forth, until 3, 2. Then when it equal to 1, your call this function, when n equal to 1, you will run this line. Then that is the recursive function. Yeah, where's my pen? Okay. Where am I? So you can see every iteration. So this one, for each recursive call, when n greater than 1, let's say this portion, the cost is C1. Yeah, every time you call, you cost you C1. Yeah, then the last recursive call costs you C2. Then the number of recursive call, yeah, there are how many recursive call? We are starting from n. Yeah, so n minus 1. 1 call, 2 call, and so on and so forth, until n minus 1 call, you will reach 1. Yeah. So it's n minus 1 call. So the number of call is n minus 1. Then each primitive operation, yeah. Here you do C2, you take C2 constant times to do the most of the recursive call. You do it C1 for most of the recursive call. Then the last one, the very last one, the base case, you take C2. So yeah, then you just sum it up. Because C1 you do it n minus 1 times, and then the C2, the last one, you do it 1 times. So total is, this is the time complexity. Okay. Yeah, it's a bit. Okay, 268 today. Okay, so this is the factorial recursive function. Blue line, when n is a huge number. Yes, when yeah, you're not surprising. I think we have mentioned a few times earlier. This thing, you look at it, C2 is a constant time, C1 is a constant time, but my n can be very, very large number. So once your n, yeah, so you can see this linear, this is a linear function. So when your n going bigger and bigger and bigger, this C2 is negligible, because this one will dominate. the whole term. Yeah. So you can see another example. Example 2, we're trying to count how many A in this array. So that means I got an array, some array. Maybe in this array I got something. There's an A here. Yeah. Somewhere gets another A here. Yeah. So maybe I got 2A in the array. Then this one, they always check the first element. Yeah, this one, as long as your size, this is the first one is the array, the second is the size of the array, the third one is the item used, the search key. So as long as your n is not equal to 1, you definitely will trying to run this line. Then you're trying to check the first element of the array, is it equal to A or not? Shouldn't be. No. C1, should C1 be negligible also? I would say that C1 is not so important. Yeah, Roy Chalmers. Yeah, so C1 is not so important, but C2 can be ignored. Because once n is very, very large, it's a very large number times 2 or very large number times 3. Yeah. You cannot set, you can totally ignore this C1. But I would say that C1 is not so critical because no matter how, this is a linear function. Whether C1, what is the number of C1? It's just a constant number only. But C2 is something you can think that is negligible. It's very small. Yeah, this thing we will cover later after this recursive function about the order of growth. Yeah. So back to these things. I think today delay quite serious because always I see your question is upper 10 to 20 minutes, 10 to 20 seconds later. Yeah, sorry about that. Okay, back to this. So if n is greater than 1, every iteration you were trying to search the first item A. Then whether the first item is equal to A or not. If equal to A, you will 1 plus. Then you recursive call. You start from the second item. Then n minus 1. You reduce this array because you already removed the first one. So you start from the second one onward. So your size will be reduced to n minus 1. Then you search the A again. So every iteration you check the first item. Then you reduce your array size. You check the first item. Yeah, if equal to A, then you increase by 1. If the return value will increase by 1. If it's not equal to A, you won't increase by 1. Yeah, so you will keep recursively do this thing until you reach the last element. When you reach the last element, then you are trying to check the last one. If it's equal, you return 1. If it's not equal, you return 0. After that, the summation start working. Yeah, they just sum it up, the things, and then return sum, then you return. Eventually, the final output should be the number, how many A in the array. Okay, that is this algorithm. So now we want to count how many comparison. I want to count how many comparison means that I want to count how many this one and this one only. Yeah. This thing is not what the question want you to do. We only want to compare the array with the search key. The array element and the search key. So this is like trying to compare between an array element and A. How many comparison are they? So if you check the algorithm, I should have 2 hours. Yeah, so when you n equal to 1, actually there's only one comparison. There's only one comparison. So every recursive call, you find that they only do one comparison every iteration. So when my W is 1, that means when n equal to 1, I only did one comparison in the base case. So when you have n element, you find that based on the algorithm, is every times before you do the recursive call, you do one comparison. So that means I need to find out one comparison in this recursive call plus the n minus 1, the how many recursive call are there here, and then inside definitely also got 1 plus the following one. So yeah, that means every time you call this function, yeah, you want to find out how many comparison are there in this, plus itself got 1. So this one, n minus 1, inside you did how many comparison? You also did one comparison. And then it's one comparison plus n minus 2. Yeah, the W n minus 2. This recursive call. This one, at this moment, I don't know how many are there. So I keep iteratively do this thing again and again. Yeah, that means I'm trying to backward find out how many comparison are there. Yeah, keep doing it. Eventually, I reach the base case W1, yeah, which I know that is equal to 1 also. No, the question, you take notes. What is the question here? I'm trying to compare the number of comparison between an array element and A. So n equal to 1 is not considered in this question. Okay. Yeah, the compare between an array element and A. Between an array element and A. So take notes of the question. Don't miss out this line. Yeah. So in the end, how many comparison are there? You are trying to sum it up this. So you expect how many 1 are there? How many 1 are there? Today delay is quite bad. If you can see that every iteration, can you do the time complexity for the? Okay. So yes, hash set correct. It's n minus 1. Here got n minus 1, 1. Then plus the last one, the base case. So total there are n iteration. There are n minus 1 recursive call. But when you reach the base case, there's another one more comparison. So total is n in the end. Yeah. If you want to analyze the whole algorithm, actually you need to consider quite a number of things, because there's an if-else statement implied that you need to consider the best case, worst case, and average case. Yeah. I think I may run out of time if I do that. Yeah, maybe we can. Yeah, you can send me an email, Smell. Yeah, then I can answer your question separately. Yeah, but I suggest you all can go and try if you want to analyze the whole algorithm. It's not difficult. Yeah. The key is that you need to do this kind of process to find out the time complexity of a recursive function. Yeah, this method called method of backward substitution. Basically, you're trying to start from the n term, then write out the recurrent equation, and then iteratively solve the problem. Yeah, you keep backward substitute the smaller one, yeah, smaller n, yeah, until you reach the base case. Then you can backward substitute. That's so-called backward substitution. Okay. What is the A? A is just a search key in this question. They're trying to search what, yeah, you can think is a character, integer, doesn't matter. Depend what is your array is. Your array is an integer, that means A also is an integer. I think in this question, A should be an integer. I remember they mentioned it. Yes, A is an integer. So some integer number. Then you're just trying to search every element in this integer array. Yeah, which one is equal to A? Okay, so this is the backward substitution. Another way is the forward one. Next one. Yeah, for example, you have a tree. Yeah, in this question, I just want to consider how many multiplication are there. So you look at this algorithm, there's only one multiplication here. So this thing, what it's trying to do, let's say I have a tree. Structure, I have a tree structure. Okay, maybe one more. So what this thing trying to do, every time whatever here, you multiply by 10. Then these two, we're trying to do the same thing for the left subtree and right subtree. Yeah, every time you times 10, then apply the same algorithm on the left subtree and right subtree. Yeah, until your tree is empty. Yeah. So in that, similarly to the previous example, you're just trying to count how many. Every time you only do one times. Every recursive call, you only do one multiplication times 10. Then after that, you will call you will become a subset. It's a subproblem. It's a left subtree and right subtree. And then every time you keep times 10 for the root, and then pass the left subtree and right subtree. Yeah, until you find out, you reach the bottom, the leaf, which is the last one you times 10, and after that you get the empty tree. This is the empty tree in the end. Always there's a now, then you will stop. So yeah, in that, yeah, we know that let's say let WK be the number of multiplication for a tree with the depth, with a K depth of, I think this is, if I said this is K equal to 1, the depth of the tree, this level, then there's in this level is K equal to 2. Then this one is K equal to 3. Okay, so yeah, let's say my WK, I think this one is the W3 like in this example. I'm trying to looking for the number of multiplication of the tree. Yeah, actually not surprising. What this thing trying to do, in short, you are trying to count the number of nodes, because every node you are trying to multiply the item by 10. So if here got 1, 2, 3 nodes, 4 nodes, 5, 6, 7. Actually, you already can see the pattern. When K equal to 1, you got 1 nodes. When your depth is 2, you got 2 power 2. You will find that it's like 3, which is 2 power 2 K. 2 power 2 K minus 1. Right. Yeah. You can, through the observation, you can find out that this thing. Of course, you can use a backward substitution. Also, you can prove it that it's a 2 power to K minus 1. But I'm trying to do the other way. Yeah. Okay. First, the base case, when K is 0, means that it's an empty tree. Yeah, nothing inside. K equal to 0. Okay, take notes. Different book, they define the depth of the tree slightly different. Here, we define that when K equal to 0 is an empty tree. Yeah, some book may be different, slightly different. Yeah, some book may be define there's 1 node inside when K equal to 0. But in this lecture, in this module, we define the tree. Yeah, k equal to 0 is the empty tree. Yes, so you expect W k equal to 1 plus the left subtree, the number of multiplication in the left subtree, plus the number of multiplication in the right subtree, plus itself 1. So this is the total number of multiplication for the WK. Yeah. Then the question is, yeah, this is, okay, then now I'm trying to use the forward substitution to do the things. So when W equal to 1, it's only one node. K equal to 1. Yeah, you only have one node here. You only have one multiplication. When K equal to 2, it's 1 plus W1 plus W1. You have 2 when K equal to 2. In this example, this one is this one. Is this. You do one multiplication. Then this subtree, the right subtree is W1. The left subtree is W1. The right subtree also W1. Yeah. So total is 1 plus. This also 1, this also 1. So total is 3. Yeah. Or you can think that that is 1 plus 2W1. You got 2W1. Similarly for, yeah, when k equal to 3 in this example, so it's like 1 plus 1, you get 1 subtree which the depth is equal to 2. Another right subtree which the depth is equal to 2. Yeah, then plus itself. There's one multiplication here, times 10. So it's 1 plus W2, W2. Then I from the previous calculation, I already know W2 is equal to 3. So it's 2 times 3. Yeah, you find that it's equal to 7. Yeah, you keep doing this, soon you will realize that this thing is 1 plus 2 plus 4 plus 8 and so on and so forth. It's a geometric series. And then you sum it up, it's 2 power to k minus 1. So, I think I use it. Sorry, am I open the wrong one? This card. Oh, yeah, sorry. I think I changed already. Should be this far. Okay, this part is the same because I add one more line here. Okay. Okay, same thing. In fact, more precisely, after you've done this, yeah, you should apply, it's a hypothesis. I guess that this thing is 2 power to k minus 1. Through the observation. Yeah, so actually, you should apply the mathematical induction to prove that it's indeed 2 power to k minus 1. I think the proof is in the lecture notes too. Yeah, you can go and take a look how to prove this thing. Yeah. So that is so-called the method of forward substitution. You start trying to, I think it's in many students asking about the lambs. A lot of lamb question, you can use this approach to solve it. You start from the small number, and then you try the base case. Then you increase by 1. Then you try 2, k equal to 3, 4. Then after that, you will find there are some, you can choose some observation and then figure out what is the general term. Yeah. And then you, okay, if it's MCQ, is fine. You can just guess that this is the correct. But if it's a proper way, you're supposed to use the mathematical induction to prove that it is correct. Yeah. That means you need to assume the base case. Yeah, first you verify base case is correct. Then WK is correct. Then you need to prove that WK plus 1 is still correct. Then that means this thing is always correct. Yeah, that means this hypothesis is correct. Yeah. What is the value? It can be anything. The key is I just want to count how many multiplication. This is just for illustration purpose only. Okay. Okay, these are method of forward substitution. Yeah, the previous one called method for backward substitution. These two basically can handle the first order recurrent equation. Yeah. Next, we trying to something more difficult, and this thing is not covered last year. I just add in, so that's take notes. Yeah. So when you encounter this is a Fibonacci. Yeah. Yeah. So n equal, okay, I think you in the very first lecture we already cover the Fibonacci. I think you also have learned it. I guess you learned it in your high school. Maybe you heard about Fibonacci sequence. You also heard about it in discrete maths. I guess they cover the recurrent equation. This is definitely very classic recurrent equation. The base case is when n equal to 1. Yeah, your Fibonacci is 1. When n equal to 2, also 1. When n equal to 3 is 1 plus 1, which is 2. When equal to 4 is 1 plus 2, which is 3. Then 5. Then 3 plus 5 equal to 8, and so forth. So this is what this function trying to return. It's trying to return the Fibonacci sequence. Yeah. So now I want to know the time complexity of this recursive function. That's why I'm trying to find out how many function call I have done in this recursive function. So if my problem size is n, yeah, definitely here I need to know how many recursive call here, how many recursive call here, plus itself, plus 1. Okay, I know that if my n is equal to 1 or my n equal to 2, there are only one function call, itself only, then you stop. There's no recursive function. Yeah, when the base case. When you are here, you only do 1 times. You only call, itself only call 1 times, then return 1, then finish. Yeah, you find that you want to solve this thing, you can go and try. Yeah, doing the forward substitution or backward substitution, you find that you cannot solve this. Because you can find that this thing and this thing, you will keep derive. Yeah, thing will get more and more complicated. You got n minus 1, n minus 2, n minus 3, n minus 4. You cannot remove them. Yeah, they will keep roll and roll and roll and roll, and then always still there. Yeah, you cannot eliminate. So to solve this problem, you need to use some method. Yeah, let's say we try what you can do based on what you learn right now. The best I can do, probably I have to make some assumption. I have to assume that this thing and this thing is about the same. Yeah, I have to make this assumption. Then, yeah, only when this scenario, then I can try to apply the backward substitution approach. Then you can try to expand this thing. Yeah, try to expand this thing to 2w n minus 1 plus 1. And then this one, you can further become 2w n minus 3 plus 1, and so on and so forth. Keep doing this. Then keep doing this. You will find that until you reach the base case, which is w2 equal to 1. Yeah, when your n minus 2, n minus 1, n minus 2, n minus 3, n minus 4, 5, 6, 7 to n minus 2. N minus n minus 2 means that it's w2. Yeah, this one I know is equal to 1. Then you can find out that here it should be 2 power to n minus 1, 2 power to n minus 5, and so on and so forth to 4 plus 2 plus 1. Yeah, this one should be 2. N minus 1 is times 2. N minus 2 is 2 power to 2. And this one is 2 power to 3, Wn minus 3. So this one should be n minus 2, yeah, w2 plus 1, and so on and so forth. and 2 power, and this one times, this one times 2, you get this. 2 power to n minus 3 times 1, you get 2 power to n minus 3. Then the rest. So this is a geometric series. Geometric series, you have learned it. Then the answer should be, you got how many terms? 1 plus 2 plus 4, 2 power to 0, n minus 2. So should be n minus 1. You got n minus 1 term. So should be 2 power to n minus 1 minus 1. Okay. So it's an exponential. You can see that this is a exponential function. Okay. It's a geometric series. Of course, I have to say that this is not very correct. Because this assumption, when your n getting bigger and bigger, you find that this thing and this thing are not really equal. Why I need to do the approximation? If today I don't know what is the next thing I'm going to cover, you only know backward substitution and forward substitution. In that scenario, you only can use the backward substitution. You have no choice. You have to make this assumption. Otherwise, you find that you cannot solve this recurrent equation. In that assumption, you will find that you cannot get the very accurate, the exact time complexity. You're only trying to do the approximation. So, okay, maybe someone cannot understand. The key is when I reach this one, I find that I cannot simply do the backward substitution. If I want to use the backward substitution, I have to do this approximation. I have to make the assumption that saying that this thing and this thing are about the same. So to do this, then after you make this assumption, after you do this approximation, you find that this thing, okay, you can apply the backward substitution. So you can just substitute this thing, Wn minus 1, a bit difficult for me. Wn minus 1 actually is 2. Actually here you also do another approximation one more times. So that's when this thing actually is very bad. You keep doing the approximation here in every equation. 2 times n minus 1 plus 1. So you substitute this, backward substitute this into here. So it becomes 2 times 2. So it's 4, 2 power to, you expect this thing will be equal to 2 power to 2 W n minus 2 plus 2 plus 1. Then you further backward substitution Wn minus 2, which is, you will get this, which is equal to 2 power to 3 Wn minus 3 plus 2 power to 2 plus 2 plus 1. Then you keep doing this until the end, you reach the base case W2. Then you can substitute and get the geometric series. When I point the cursor, okay, I try. I think maybe not clear. I trying to put the laser out. Okay, so so you get this geometric series. I think I have to adjust. Okay. So this is 2 power to n minus 1. Anyway, I just show you how to use. Actually, this one I just want to show how to do the backward substitution. But I have to say that this assumption is not very correct. Because Wn minus 1 and Wn minus 2, they are big different. Actually, when your n getting bigger and bigger, the difference is getting bigger and bigger. So actually this assumption is not very valid. So for this type of question, this is not a good idea to do it. But here I derive it for you. It's just let you see how to do the backward substitution only. Yeah, for this question, you find that you cannot do this. Not good enough. There are better way. Yeah. So can we solve it exactly? It's possible. You can solve it exactly. Because you have learned the second order linear recurrent with constant coefficients in the discrete max. Yeah, I can use that method to solve this problem. So recall what you have learned in discrete max. Actually, you can rewrite that recurrent equation in this format. In this form, AWN then plus BWN minus 1 minus, should be plus. I got the typo here. Discuss, I should say is plus. Okay, so I can write it in this format. So if the ABC is a constant coefficient, then in this equation you only have the n, the biggest one is Wn, the smallest one is Wn minus 2. The difference is 2 position apart. So this is a second order. So this is a second order. Then if my Fn is equal to 0, which is called homogeneous recurrent. If its Fn is not equal to 0, otherwise, that means it's non-homogeneous. Okay? I think in the discrete max, they only cover the homogeneous. Here, I need to use the non-homogeneous. So there's one more step further to solve this equation. Okay, let's see how. Okay, I made a typo. This one should be plus. Okay. See? I think I already changed it. I don't know why. I think I opened the wrong file. Never mind. This one should be this way. Okay. Yeah. So when you learn the discrete mathematics, they already tell you that to solve this thing, the homogeneous version, that's why I consider this as 0. Yeah, I need to find its characteristic equation. So its characteristic equation is AR squared plus BR plus C equal to 0. Then you just solve this quadratic equation, the formula, standard. Yeah. Then there are a few possible. This root can be 2 real and distinct root. Yeah, this root can be 2 real and distinct root. And then you also can have, I think the cursor should be, I think laser better, right? Yeah, no choice. Yeah, this is the biggest things I can show you. There's another second scenario. It can be a real root. Then the third possible is the 2 distinct root. Yeah, that means this will be a complex number. This thing is depend on the b squared minus 4a. So if b squared minus 4a greater than 0, you definitely get 2 real. I think the old notes, I think I already update the lecture notes. Here there's a mistake. I typo, should be only C only, the characteristic equation. Yeah. So when you have a real double root, that means this thing b squared minus 4ac should be equal to 0. So I think this thing you should learn it in secondary school. So what is the corresponding homogeneous solution? Yeah. Oh yeah, this thing correct. Okay. Oh, okay. I know the reason. I got 2 slides. I've only changed 1 slide. I forgot to change the other one. Okay, so yeah. Okay, so in the next slide, this one is correct. So it should be C. So this one, the homogeneous solution. Later I will update the slide in the NTU Learn. I think I make some typo here. Yeah. So you find that if it's the 2 real distinct root, your homogeneous solution will give you is a 2 geometric series. Yeah, r power to n and the other r minus power to n. Yeah, you can think that this is a 2 linear combination of 2 geometric sequence. Okay. Yeah. So if it's this one is the 2 double root, then your homogeneous solution should be r power to n, and the other one should be a r geometric sequence, n times r power to n. Okay. Then the last one should be similar to the first one, just it is a complex number. Well, I can rewrite it. I also can rewrite it. Here I just rewrite it in the trigonometric form. Yeah, actually it's still a complex number. Actually it can easily derive. Yeah, so the first one and the third one actually is the same. Just one is the real. The other one, the third one is a complex conjugate root. Yeah. Then the second one, because it's only one root, yeah, so one of them is a geometric sequence. The other one you expect is a r geometric sequence. Yeah, this one is n, so that means it's something 1 times r power to 1. Then 2 plus 2 times r power to 2. Then 3 times, yeah, so there's a arithmetic sequence combined with a geometric sequence. Then, okay, so, but now my problem is like, I need to solve the non-homogeneous solution. Okay, this is something new to you, maybe some of you know it. Yeah, when this thing is not zero, yeah, you have some function in this format, KRPN. Yeah, that means there's another geometric series, yeah, times some constant. Yeah, if your function is in this format, you expect that your general solution is not only the homogeneous solution. There's another particular solution you need to find out. Okay? Yes, you need to remember this formula. So take notes. So there's a 2 term. Just now you already find out the homogeneous solution. You need to note that actually because of this thing, there are another part you need to find out, which is the particular solution. So this particular solution, how to find it? You need to know that this RP, if this RP is not same as any one of the characteristic root, then this particular solution is a constant a times RP power to n. Plus, yes, it should be a plus. It should be a plus. Sorry. I think I copy wrong. Okay. Yeah, should be plus here. Thanks. Yeah. So if this is the first case, when this RP is not equal to any one of the root, then there's another scenario that this is one possible. Then another possible is like when this RP is equal to one of the root, either the positive one or the negative one. Yeah, then in that scenario, your particular solution is a R geometric sequence, nRP power to n. My God, this is the R plus and R minus is this one, which I show. Yeah, it's the R plus. I call it R plus and R minus. Yeah. So if they are. So this is a homogeneous one, then particular one. Then there's a third possible. It's like you only have one root in your characteristic equation. Yeah. Then this RP also equal to that root. In that scenario, you expect that your particular solution is the n squared RP power to n. Yeah, you can see that from geometric become arithmetic. It become this one. I also don't know how to call it. Yeah. Yeah, n squared times r. So you can see every time you will just add one more n in front. Yeah. So this is the particular solution. Okay, I think I will overrun. I have to accelerate. So back to just now the Fibonacci equation. I can rewrite this equation. Give me a laser. I need to rewrite this thing into this form. I rewrite it to Wn. I just move this Wn minus Wn minus 1. So actually, this is a second order homogeneous recurrent equation. I'm trying to find the homogeneous solution and the particular solution. So I have to be fast. So the homogeneous solution, you can find the characteristic equation is -1 plus minus square root 5 divided by 2. So yeah, you substitute back to the just now the lookup table. Yeah, they form two geometric series, the linear combination of two geometric sequence. Yeah, one is the 1 plus square root 5 divided by 2 power to n. The other one is the 1 minus square root 5 divided by 2 power to n. Yeah, but alpha and beta at this moment, I still don't know. Yeah, later I need to find it. Okay, this is the homogeneous solution. Then the particular solution is 1. So I can set that this is equal to 1. The Fn is equal to 1 times 1 power to n. Whatever n is always still equal to 1. So I can rewrite it in this form so that I can substitute it back to just now the lookup case. Yeah, so this one is 1. So it's not equal to any one of the root. Right? So it should be the first case. In that scenario, I expect that this is a times 1 power to n, my particular solution. So actually now I got the homogeneous solution and particular solution. Yeah, this is the solution, but I don't know alpha, I don't know beta, I don't know a. I need to solve these three unknown. So how to solve this alpha, beta, and a? Okay, a can be fine. You know that this, because the homogeneous solution will give you 0 if you substitute back to the original recurrent equation. So definitely, if you substitute your particular solution back to the recurrent equation, it will give you equal to 1. And I know that this particular solution is a constant sequence. It's always equal to a. Whether it's n or n minus 1 or n minus 2, it's always equal to a. So you know that this is a minus a minus a equal to 1. So my a is actually equal to -1. Okay, then a solved. Now it's alpha and beta. I still got two base case I haven't used. So I can use my base case. Yeah, W1 and W2. If I substitute back this, so it's two unknown, two equation. You can find out your alpha, which is 2 over square root 5. And -2 over square root 5. I think I have to end. This thing I will explain one more times on Monday again. Yeah, so this is, just let you know that this is the solution. Yeah, quickly show the last slide for today's lecture. Yeah, so you know that this is a solution. You can try to verify it. Yeah, if you're trying to let your n equal to 4, actually you need 1, 2, 3, 4, and 5. You need to do 5 function call. Yeah, so if you substitute this number, you will find that when your n equal to 4, there are 5 function call. Okay, this thing I will try to explain one more times to you on Monday. I think that is the today lecture. If you have any question, you can post it here. I'm trying to answer it now. Or you can try to send me an email. Yeah, I think today there's some delay in the YouTube. It's a bit slow. When I see your response, it's already maybe 15 seconds later. Okay, thank you. Yeah, Monday, I think this part I need to explain more. I will do it again on Monday on this few slides. I will update the slide. I think I make some typo here and there. Yeah, later I will update in a short while. Yeah, this, but I think the PDF notes should be correct. Only the slide, PowerPoint slide. Yeah, I make some typo. Did you find the value R? Okay, someone asking how did I find the value R? Yeah, so if you got class, you can left now to attend your OODP. If I'm not wrong, there's an OODP. Yeah. How do I find the R? It's just a quadratic equation. Yeah, you solve the characteristic equation and then find out the R. Okay. Yeah. Okay, later I will make a double check. I think it's just a plus minus. You still can, yeah. I think when I type too fast. I miss out the things. So I suggest if you forgot what you, I think the homogeneous version, you should learn it in the discrete max. Just I find that it's not enough. Just use a homogeneous is not enough to solve the time complexity. I need the non-homogeneous. That's why I introduced the non-homogeneous here. Yes, you need to refer back. Yeah, that's why this is a prerequisite. That's why I need to add this thing, because discrete max is the prerequisite for this module. You should know this. And yeah, then you can solve something more challenging recursive function. That will be better to you. Okay. Yeah, if you have class, you can left now, actually. Yeah, I think I stopped the today section. If you have any question, you can just send me an email. I think the delay for YouTube today is also quite slow. Yeah, they're quite obvious. Oh wait, I see your question is like 15 seconds later. Yeah, what is the quadratic? That you need to find out what is the characteristic equation. I think someone is yeah, so you need to know this first. Yes. Okay. Okay. I think Monday I will explain this again. Yeah. I also cover this homogeneous one. Just maybe you can compare the discrete max. Notation may be slightly different book, different notation. I also not too sure how your discrete max notation. So I just use the book I have, yeah, and use their notation. Okay. Anyway, thank you for your attending today's lecture. That's all, and goodbye.